Hello and welcome to another tutorial on I2C Core. We have had several previous tutorials. In this tutorial, we'll be talking about the registers. You can find the full project tutorial, the LOGISM circuit, VERILOG code, and I2C Core introduction and explanations at projectfpga.com/I2C. So here we'll be discussing about the several registers we had. There are up to 8 of them. The code can be found at projectfpga.com/I2C/code.php. So we have up to 8 registers which we'll be discussing. One, we have the status register, the data receive register. We have this is not a register, this is for the slave address, or maybe we call it a register too. It stores the slave address, our own slave address. Then we have the control register. Then we have the data receive register. Then also we have the data transmit register, the rescale register, then the timeout register, and another one as well. So for this this interrupt, so whenever you have the interrupt enable bit set and you have an interrupt, where is it? Sorry, let me trace this. So watch this highlighted signal. I have an interrupt enabled. This interrupt service routine is going to come on. So that's how we have an interrupt. But there are conditions for turning on the interrupt actually. So let's talk about the status register. The status register is actually a write-only register. So it stores the status of the core. One is saves. One is when there's an acknowledge request is stored. When there's an interrupt, when there's a slave read or write, when there's a timeout. This timeout is used in the principle of clock stretching. We're going to explain that later. Then arbitration loss. I've explained arbitration loss. I told you to watch Foolish Engineer. He explained arbitration. That is when two masters are trying to transmit at the same time. The master that is talking to the slave with the lower address is going to take control. Is going to win because it's an open drain. The line is usually high. So whenever any of the bits is set 0, the slave with the higher bit address is usually the one that has more higher ones. So the one with the lower one is going to be communicated with. Then when the bus is busy, the signal is stored also. When the slave is addressed, that is when the received address matches the slave address, this slave address bit comes on. Then this byte trans also, when the byte has fully been transferred, that is when the bit counts up to 8. So all these are what is being stored in our status register. Then also we have the receive register, that is the I2C data we received is being stored here on next clock pause. Then again, this is where we store our slave address. So for us to edit any of this register, we can use this signal here. The signal AS. We use this to signal AS and DS to edit the registers. So let's take for instance, let me say, I'll show you how it's being used. So this is it here. it comes all the way from the top and goes down to here. You can see it enables, see I've highlighted this, it enables all the enabled bits of the registers. All this, see, it's coming from the AS. The AS is used to enable all the enable. This is the rescale register enable, control register enable, status register enable, timeout register enable, address register enabled, data register enable, received data enable. So all these enable bits are used to enable each of the registers, and you can see here that just like I said in the last tutorial, you'll be seeing this sig at the end, signal added at the end, because they are the outputs here. That is conventionally for this particular tutorial, but when they were used to turn on the registers, as can be seen here, the sig were no longer there, but you still have to join them together. See, the sig is no longer there, but in the upper top of this sub-circuit, we are going to join them together. So once the slave address has matched and we receive the particular register address we want to talk from the master, it's going to be stored. The address is going to be stored in this address bus, and then we start comparing it with the address of all the registers to know which of them is matched. So it compares with, this is the address of the prescale register, this one 04 is the address of the control register, 08 address of the status register, and so on and so forth. So whenever it matches and this AS signal, remember this signal, AS signal is on, therefore we are ready to write to the registers. This is status register, then again. So remember, this is it here, that AS. So you can see it is turning on, in as much as it has already turned on the enable signals. So that is how these registers, different registers, are being manipulated with using the enable bits. See this one, the control register enable, timeout. Timeout register enable is timeout register, actually this is the timeout signal, is used during clock stretching. You know, clock stretching is used when the slave is too busy to receive more data. It pulls the SL line down for a while, so when it's ready to receive, it releases it. But this timeout register stores the maximum time the slave can pull it down. So when the slave pulls it down more than this required time, this timeout register, once the time exceeds the time that is stored in this timeout register, everything goes back to data lost. The transmission is lost. So that is the things you are going to find when you are going through the code. So another thing, then also at the end is the main controller interface. Let me show you the control register. Remember this control register, this is all the bits of the control register. Is that what it holds? It holds the interrupt request, halt request, interrupt reset, repeated start, acknowledgement, master read write, the mode, interrupt enable, call enable. So that is why it's called the control register. Then also this is where we joined the main I2C core with the controller interface. And finally, this is what this sub-circuit looks like. So as I was saying, let me make this a little bit clear by let me delete this reset first, and then the clock. So now let me highlight this. Let me highlight this SDA output. Okay, you can see that this SDA out, I joined this. That is one transmitting the SDA out and the SDA in are together. The same for this SDA in, SDA out. This is because they are bidirectional. Within the sub-circuit, there are two, the in and the out, but outside we call it SDA line. The same goes for the SCL. You have the SCL out and then the SCL in. So the two of them are joined together and named SCL. So because it's a bidirectional circuit, so whenever you are designing this circuit, please bear in mind that they are not just single in and out line. They are actually bidirectional. So I think that's all for this. Thank you. When you go through the tutorial, when you go through the code on the website and you find any more questions, kindly send me an inbox. Thank you. Subscribe to my channel. This is projectfpga.com. Thanks for watching this. You're welcome. projectfpga.com.